This is section 6.7, steps to solving radical equation. There are 4 steps that are involved with solving radicals. The first one is to isolate the radical on one side of the equation. The idea here being that anything that's not under the radical sign, whether it be a variable or some sort of integer or even a decimal or fraction, should be moved over to the other side in order to get the radical by itself. It does not matter whether you choose the left or the right hand side of the equation. The second number here says raise both sides of the equation equal to a power of the index. You notice down here, if we remember what a radical looks like, the index is the little number that occurs where the circle is, and the idea there being if it's a square root, it's inherently going to be a 2. If it's a cube root, it's going to be a 3. A fourth root, it's going to be a 4, so forth and so on. That's the power that we want to raise both sides of the equation to. Step 3 is solve the equation by getting the variable by itself, and here the idea is when we start to work with the equation, we have to decide what degree we're working with. If we have a linear equation or an x to the first power, it's kind of standard operating procedure. We want to get the variables by themselves on one side and get the numbers on the other side. If it ends up being an x squared or higher, the idea is to set the equation equal to 0 and try to factor. On step 4, check your solutions. This is something that was optional and we always suggested that you do it. But the idea now is that we can have something that are called extraneous solutions. So what's going to happen is we could end up with a possibility where we end up with one answer and we plug it back in and it does not work. It's also possible to end up with 2 solutions, and it's possible to end up with no solutions as well. We just don't know until we plug the numbers back in to see what ends up happening. It's kind of up in the air until we actually do that substitution. So if we go to an activity here, solve the equation containing one radical, you notice that step 1 is complete and that the radical is by itself. So there's really not much to do there. If the 4 were over on the left-hand side, we would have a problem, but we're in good shape the way it stands. You notice that in step 2, the index, being that it's a square root, is a 2. That's why we chose to raise both sides of the equation to the second power. The idea being that as soon as I square the square root's going to become a first power, which means there's no need to have a radical around it anymore. The 4 squared becomes a 16, and this is what we had talked about down in step 3 where you solve the equation. You'll notice that the only thing we really need to do now is to push the 2 over to the other side and add it. We get an 18, and then to get the x by itself, we simply divide by 3 to get x equals 6. To complete step 4, you'll notice down here we did a check, which means substitute the 6 back in wherever you see an x. So we plug the 6 in, we end up with 18 minus 2 is equal to 4, the square root of 16 is equal to 4, and 4 equals 4. So we found that the solution that we ended up with is not extraneous, and in fact when we plug it back in we have one solution. When we get to our second activity here, solve the equation containing one radical. There's still one radical, but step 1 is not complete. It's not a big step, but it's something that we have to watch out for. When we go to solve for x, we notice that we have to move the 5 over to the other side and get x plus 5, leaving the square root by itself. Very much like the last problem where we end up with the square root of 1 minus 4x quantity squared is equal to x plus 5 quantity squared. The one thing we need to remember over here, and this is an important step because this is where a lot of students make mistakes, is that when we go to multiply x plus 5 times x plus 5, it does not become x squared plus 25. In other words, that 2 does not go over top of the plus sign. And you'll notice that there's a little note out here that we must FOIL this together. And we take x times x, we get an x squared, which is down here. We get 5x and 5x give me my 10x. And then 5 times 5 is simply 25 at the end. The 1 minus 4x, as we said before, the radical is going to disappear. And the thing we have to kind of be aware of right now is that we have an x squared equation, which means that we're not going to be necessarily pushing everything over to the one side. In fact, what we're going to try to do is set it equal to 0. And at this point, what we're going to do is set it equal to 0 and try to factor the problem. Noticing that it's an x squared and there's a 1 in the front of the x squared, The question I'm really asking myself is, can I find two numbers that multiply to give me 24 and add to give me 14? And it certainly can. If I take the 12 times 2, I get 24. If I take the 12 plus 2, I end up with my 14 in the middle. These are both contenders to be solutions for the x up in the original equation. So I simply come down and say x plus 12 is 0 or x plus 2 is 0. And this is what we did at the end of the polynomial chapter where we solved x squareds. We find out that x equals negative 12 or x equals negative 2. The question is, do both of these solutions actually work out to be solutions for the original problem? If I come down to check number 1, I can see if I plug in a negative 12, I get 1 plus 48 is 49. 7 minus 5 is going to equal 2. But we're looking for it to equal negative 12. Thus, we find out that negative 12 was extraneous. So even though it ended up being the algebra was correct, we didn't do anything wrong, we're finding out the negative 12 does not substitute back in. It's possible right now that if negative 2 doesn't work, we have an empty set. If we plug negative 2 in, wherever we see an x, we find out that we get 1 plus 8 is 9, square root of 9 is 3, 3 minus 5 is negative 2, and we end up with actually a true statement at the end where we have negative 2 is equal to negative 2. So we can say that we do, out of two possible solutions, we found that one of them works, and the one that does work is x equals a set that contains negative 2. So we can't be in a big hurry back here to kind of circle both of these and say that they both work, as we see that one of them doesn't and the other one does. In our last example here, our last activity, we're going to notice something slightly different here. You'll notice that we have two radicals. Note step 1 is not complete. The radical needs to be isolated. Since two radicals exist, we must isolate one, then square it, and then repeat the process with the second radical. So the idea being that we want to take one of these at a time and push them over to the other side, but we can't do them both. And in fact, the last thing we want to do is square the left-hand side first. That's a very common mistake because the idea is there we have to FOIL it, and in fact that's not going to get rid of radicals for us at all. So what we want to do is pick one. It doesn't matter which one. We can take the 2x minus 1 and move the x minus 1 over to the right-hand side. You notice again what's happening is very similar to the last problem. This is squared, which gets rid of the radical. But on the right-hand side, what we're finding is that if I square the right-hand side, I have to be careful to use a FOIL process here. And I have to think this through. If I take root x plus 1 times root x plus 1, that's the same thing as squaring it, which is just going to give me good old x minus 1, and a root x minus 1 gives me root x minus 1 squared. And so I find out that gives me good old x minus 1. If I take 1 times anything as itself, 1 times anything as itself, and I find that I have two of these, so now I can say 2 root x minus 1s. And then finally the last term is 1 times 1 gives me 1. And that's where this line comes from. It's just that FOIL process. But again, we got to make sure that we're FOILing it and we're not just taking that 2 across the plus sign. So the idea is right now I want to repeat the same process where I take everything over to the other side and get the radical by itself. So this one and this one add to 0. The only thing that really needs to move is going to be x. And when I move that over to the other side, 2x minus x is equal to x. And I still have my negative 1 from before, but now look at the right-hand side. My radical's by itself. So the idea is that I need to square it. If I square both sides, the left-hand side is FOIL again, but we got to remember the middle term comes out. 2 squared is 4, and the square root of x minus 1 squared is x minus 1. If I distribute, I get 4x minus 4, and the left-hand side stayed the same in that step. I'm noticing that I have an x squared, and so the idea is both of these terms on the right are going to go to my left, and I'm going to set it equal to 0, and hopefully be able to factor. I can factor it down. Two numbers that multiply to give me 5, and add to give me negative 6, negative 5, and negative 1. So when I solve those, that'll give me 5 or 1 as a solution. It's possible that none of them work, one works, or they both work. If I come down to check, I find out that if I plug my 5 in, I get 10 minus 1 is 9, 5 minus 1 is 4, 3 minus 2 is 1, and 1 equals 1, which means x equals 5 does work. If I plug my 1 in, I find out that I get square root of 1, square root of 0. Well, 1 minus 0 is also 1. So I'm finding that I have two solutions to this problem. I'm finding that x equals 5 and x equals 1 are my solution set. But I didn't know that up here until I actually went down and checked. Checking is an important step, as we saw in the previous example. It is possible to get extraneous solutions, so we must remember to go ahead and do that for each and every problem.